Earthquakes strike with no warning and cause billions of dollars in damages. Worst of all, they can end lives. But there's one simple construction material that could ensure everyone walks away safely. Let's test it out.
Christchurch, New Zealand, 2011. A 6.3 magnitude earthquake kills 185 people.
All of the buildings in Center City, Christchurch, that were hit with that earthquake, when they were founded on helical piles, they survived. And all of the buildings that were founded on concrete failed.
Helical piles are thin steel shafts often used to stabilize structures in seismic zones.
When we have a helical pile underneath a building, we might have permanent structural damage, but we won't have life lost because the people will have a chance to get out.
Geotechnical engineer Amy Serrato wants to know just how strong helical piles are.
We know they work well because they're slender, they're ductile, and they damp the earthquake motion as it comes up through the ground. But we don't know how much and how that connection to the building really works. And so we're looking today to gather all of that data.
For this test, Amy's come to the world's largest outdoor shake table at UC San Diego.
This data is going to be the first of its kind. We've never done a seismic test on helical piles ever.
Amy and her team have filled each of these 1,400 kilogram skids on top of the shake table with 10 4-meter-long helical piles and tons of sand. Giant actuators will launch the skids back and forth at high speeds to see if the helical piles move.
We are going to throw the 1994 Northridge earthquake at it and the 1995 Kobe Takatori earthquake, which has huge displacements, and we want to see these buildings rock.
Northridge 75% in 3, 2, 1.
We're looking to see the maximum deflections for the magnitude earthquake we're placing on it. We put a 50% earthquake on it. We measure the deflections, the bending moments, and then we put a 75% earthquake on it, so kind of like an aftershock.
Wire cables connect to the strain gauges to gather data.
From the strain, we can calculate axial load, we can calculate bending moment, and then from the accelerometers, we're measuring the G-force.
Northridge 100% T0 in 3, 2, 1.
The piles look like they're holding up pretty well. All right. Now we move to the Takatori. Takatori earthquake will be much bigger than the Northridge because the displacement is a lot bigger. So this was a 6.7 magnitude earthquake, and the Takatori, the Kobe, will feel like an 8.9. If anything's going to fail, it'll fail during the Takatori earthquake.
Takatori 75% in 3, 2, 1.
Whoa! It's a lot of movement. That's not even the biggest one you're going to see. The next one is even bigger.
Takatori 100%.
That's pretty impressive. So if we had that much movement with that much concrete, the concrete would have cracked. And so then you're done. You have to take down the building and rebuild it. There's no healing that. For the last shake of the day, we're going to pump it up to 150% of what we've seen on Earth and see how the piles react to a magnitude 10.0.
For this one, Amy heads up to the control room where all of the data are recorded.
In 3, 2, 1.
That's one of the biggest earthquakes in the entire world. If the building can withstand something of that magnitude, then we have a better chance of getting all the people out alive. With every research project, we have 1,000 more questions now than we did when we started. And so we really hope to find out more about how these helical piles react in different scenarios. The piles seem to have no bolt hole elongation, so that's great, and no permanent deformation. They're perfectly vertical. That's what we wanted to see. We've proven through this test that helical piles can take shake after shake after shake. Hopefully, we won't have as many lives lost across the world if we build a better foundation and a better structure.
Now, you might think it's weird that Amy studies earthquakes but lives in Oklahoma, but get this. Oklahoma is actually the most seismically active state in the United States right now because of fracking.